All right, good afternoon. Welcome to the Best Paper Award session. We will have 1 hour, we will have two presentations. First, the presentation of the Best Paper authors, and then a presentation of the runner-up, the second place. So the Best Paper Award session, this award recognizes outstanding research that demonstrates excellence in our research field. And the selection process was highly competitive this time. We had a lot of really good papers, and the review committee did a great job and thoroughly reviewed our program and the papers. Without further delays, I would say let's begin the session by announcing the best paper. The title of the paper is Kyber / Exploiting Secret Dependent Division Timings in Kyber Implementations.
So the authors of the paper are Daniel J. Bernstein, Karthikeyan Bhargavan, Shivam Basin, Anupam Chattopadhyay, Tikia Chia, Matthias Canwisher, Franciscus Keffer, Thales Paiva, Prasanna Ravi, Gautam Tamwada. So we would like to give a warm applause to the authors. And invite the authors to come off on the stage and and collect the certificates. This is an example of multi-author paper. So I think after this we'll follow it up with a presentation from Matthias.
Yeah, thank you very much for the introduction, and thank you very much to the program committee and the chairs for selecting our work as the best paper. We're very honored. As you can see, this is joint work by a lot of people. I'm not going to read the list again. All right, preparing this talk was a little hard because it feels like this work was done quite a long time ago, and probably most people that are interested in this sort of stuff have heard of it. But I hope I can still tell you some new things today. But let's start with a basic recap of what Kyber / is. Okay, this doesn't work. Now it works. Okay, great. All right, Kyber / are actually two vulnerabilities that we call Kyber /1 and Kyber /2, and they were caused by a line of C code that was a division, so a / Kyber Q, where Q is the prime that's used in Kyber. And this division was turned into actual variable latency divisions in assembly. And actually, this wouldn't always happen. So if you optimize, and for most optimization flags, for example, O3, which we commonly use, this gets turned into a multiplication by a constant and a shift. And that's perfectly fine. So that's good. But if you use certain optimization flags, so for example, you optimize for code size, then the compiler would actually turn this into a division. It's just variable time and then leaks. So that's bad. And as I said, there's two vulnerabilities. The first one that was discovered first is called Kyber /1. This was a division in the poly2 message function in Kyber, which is used in decryption, and it clearly operates on secret data, so this leaks secrets, and you can relatively easily recover the secret key from that. The second one that was discovered after Kyber /1 is called Kyber /2, which is actually in the poly compressed function, which is used in encryption. So it's actually the ciphertext compression, but you can still mount an attack that's a PC Oracle attack. I'll talk more about that later. And these two bugs were present in the C reference implementation, but actually from there they made it into quite a few other implementations. So a lot of places had similar lines of code. And in this paper we show that we can actually do key recovery for both these two vulnerabilities. Now, let me already show you the fix. Fix is very, very simple. Just don't use a slash. So basically, nudge the compiler to always turn it into a multiplication. The way we do that is we rewrite that line into doing what the compiler would usually do when optimizing for speed. And then if you compile this under all optimization levels that we tested, this turns out fine. And many, many libraries have applied patches that fix similar lines of code after this became public. Okay, maybe let's take a few steps back and look at the broader picture of this. So as I guess 99% of the people in this room are aware, we now have post-quantum standards, and one of them is Kyber, and the others are Dilithium and Sphinx Plus. So now there is a massive deployment of these schemes. Major tech companies are rolling it out. Governments around the world are pushing for very ambitious adoption timelines for those. So a lot of things are being rolled out, and Kyber is really a critical component in this because it's the only NIST standardized CAM, at least so far, and it protects against harvest now, decrypt later attacks, so there's really a lot of urgency in rolling this out. And if you look into this in the wild, a good place to look at is Cloudflare. So they publish statistics, and there you can see that right now, I checked this a few days ago, around 40% of their non-bot traffic is using Kyber. So really trillions of connections these days are relying on Kyber implementations to be secure. Okay, what am I going to talk about for the rest of this talk? I'll briefly talk about the disclosure and the discovery of these vulnerabilities. We'll then show you how we exploit these vulnerabilities. These attacks work slightly different. And then I'll talk about how we can maybe avoid things like this in the future. I'll first talk about how we can detect this using a Valgrind patch. And then I'll talk about some other prevention ways using high assurance methods. Okay, contributions of this paper. First was the discovery of these two vulnerabilities, but they were already publicly announced before. So the main thing we did in here was actually implementing the key recovery attacks, and we've done that for 3 different platforms. For Kyber/1, we've done this on a Raspberry Pi 2, and for Kyber/2, we've done this on a Cortex M4 and on a Cortex A55. And then the other part of the paper is more on detection and prevention. And we've also done some more large-scale analysis of using our detection tools of many crypto implementations in SuperCop, and I'll show you some of the results we got in there. Okay, let's start with the disclosure. So Kyber/1 was first disclosed to the Kyber team on November 28, 2023 by Tamara, Bhargavan, and Kiefer. So this was shortly after it was discovered. It was disclosed to the Kyber team. And then very quickly, sorry, this pointer does not work very well. On December 1st, it was fixed in the reference implementation. Then about 2 weeks later, Bernstein was also looking into this and found the same problem, but it was already fixed. So he just announced it on the PQC forum that he also found the same vulnerability. But it was already fixed at that time. So then that is when we started also looking into this, trying to implement this attack. But when we did measurements on this, it just wouldn't work. So the measurements, the timings we got were just not matching what we were expecting. When we digged into this, we found another place in the code that was leaking as well. And that was then called Kyber/2. So we also disclosed this to the Kyber team as soon as we found it on December 29. It was fixed the day after, and we announced it on that day as well. Actually, on the same day, also Bernstein had got an exploit working for Kyber/1, so it was already clear that we can actually exploit this. So this was a very a smooth disclosure process. It was fixed very quickly upstream. So this is, I think, went very, very well. Yeah, so I'm very happy about that. And then afterwards, a lot of other libraries have applied patches. Here is a list on the website. There's a few more. We've not checked that all of them are vulnerable. They didn't all have the same codes. Some are even written in other languages, but they've applied patches, so the maintainers must have thought that this is something that we need to fix. Yeah, so this was present in a lot of places. Lots of code was copied from the reference places to other libraries, but luckily this was fixed relatively quickly, which is good news. Okay, let's take another step back on what are actually timing attacks. And if you look in the literature, the first paper that really brought broad attention of timing attacks on crypto is Paul Kocher's paper from 1996. And let me read you some paragraphs from this paper that are quite summarizing what I want to say about timing attacks. Crypto systems often take slightly different amounts of time to process different inputs. Reasons include performance optimizations to bypass unnecessary operations, branching and conditional statements, RAM cache hits, processor instructions such as multiplications and divisions that run in non-fixed time, and a wide variety of other causes. That covers kind of what we also think about in normal timing attacks nowadays. Divisions were already in there. And then later in that paper, he writes on how we can prevent this. The most obvious way to prevent timing attacks is to make all operations take exactly the same amount of time. Unfortunately, this is often difficult. Making software run in fixed time, especially in a platform-independent manner, is hard because of compiler optimizations, RAM cache hits, instruction timings, and other factors can introduce unexpected timing variation. So in this 1996 paper, it's kind of everything that Kyber/Slash is using is already there. He's already talking about compiler optimizations. He's already talking about divisions. So this is now almost 30 years ago. It looks like we haven't gotten very far in not having these kind of problems, which is a little sad. But maybe we have made some progress. So constant time programming is now a standard technique that you kind of expect if you get crypto code that is constant time. The way that the goal of this is to make your execution time independent of secret values, which then stops these basic timing attacks. There's three basic rules that we have to follow for this. We cannot have any secret dependent branches. Instead, we need to use some arithmetic to do the same. We cannot have any secret-dependent memory accesses, because this you can exploit this in cache attacks. So instead, we just need to avoid lookup tables, or if you really need a lookup table, you have to load the entire table. And the third thing we have to avoid is using variable time instructions. So you should not have divisions or other operations that are non-constant time. And in theory, this is easy, right? Just follow the three rules. In practice, this is still quite hard because there's compilers that do things to our code that we don't want the compiler to do with our code. And at this point, I also need to mention that this only stops basic timing attacks. Now, especially over the past couple of years, we've seen much more advanced timing attacks that are much harder to protect against, or we don't even know how to properly protect against them without fixing hardware. So how do we prevent it for variable time instructions? Divisions are really the prime examples here, so I'll stick with divisions. So how do we avoid that? We have to look at where we actually need divisions in cryptography. The prime example is modular reduction. This is used in a lot of places, and if you implement this naively, it's going to be variable time. But luckily, there are solutions to this, Montgomery reduction, Barrett reduction, that do this in constant time, and they're even faster. So that's what we use, and that's commonly done, so that's fine. Another thing we sometimes have is divisions by a constant, and here, luckily, we can just replace it by a division by a multiplication by a constant mod our word size, and that always works. It's faster, it's constant time, so there's no reason not to do this. So the expectation is sort of that the second part compilers will do automatically. That's at least what the authors of this software thought. And unfortunately, this assumption doesn't really hold because some optimization flags and some compilers break this. So let's look into the vulnerable code, the poly-to-message function. So this is the full function, but we only really care about this one line that I had on the slides earlier. And if we put this into a compiler, and we optimize for speed, then this is always turned into multiplication. And so a good tool to demonstrate this is the Compiler Explorer. I can highly recommend this tool. You can just plug in your code and play with different compiler versions and different flags. That works very well, and here we see it for O3, so everything is fine, and if you change it to OS, then you get a division. And you can't really blame the compiler here. He's asking it what we wanted to do. It optimizes for code size. This is using fewer instructions than the previous version, so the compiler is doing what we ask it to do. And here, let me stress that this is not a vulnerability that only affects a niche platform or niche compiler version. This applies to a lot of different platforms. We've reproduced this on x86, we've reproduced this on AR64 and the Cortex-M4. So this affects a lot of platforms. We also tried a lot of different compiler versions, and we've basically get this with any version of GCC when using OS and any version of Clang when you use OSAT. So this is really wild. Yeah, it's there in every version. Next, what we looked at is how do these division instructions actually leak? We looked at this on a bunch of different platforms. I'll present some more details on the Cortex-M4. And if you look in the manual for those, you will just read this instruction takes 2 to 12 cycles. But we need to look into if this actually, for the ranges of inputs that we get, this actually gives us some information. So we've done some reverse engineering to find out when these instructions take what amount of cycles. You can see it here in the table. It basically depends on the scale of the numerator and the bit length of the denominator, and it's just increasing. And yeah, you see the table, and we see that actually the first 3 rows is what matters for Kyberslash. So we see that there are some jumps in timing, and that's all that we need to actually build an attack from this. Looks similar on the Raspberry Pi 2. Here it's actually soft division, which has even bigger differences in timing for some ranges. And similar for the Cortex A55 and A72. We have tables for all of this in the paper if you ever need division timings. Now, how do we exploit this? Let's start with Kyberslash1. So the function that we're looking at here is executed on the decrypted value, so on the message. So this is actually V minus the inner product of S and U, where S is a secret key and V and U are parts of the ciphertext. And now if you look at this line of code and look at the numbers I had on the previous slide, you will see that division timing here will jump if this input value T passes certain values. So now we can build an exploit from this. So let's imagine we set all values, all polynomials of U to 0 except for 1. And that polynomial we set to 72 times x to the 100. And V we set to 208 times x to the 255. And then what's going to be computed for the decryption is going to be 208 minus 72 times some secret. And now, if the secret is very large, so 3 is the maximum value here, then this subtraction will wrap around. So the value will be very large, and this will lead to a slow division. Whereas for all other values, this is going to be between 64 and 400. So this will be a fast division. So just by distinguishing these two cases, we can learn something about the secret. If we do this with a few other values, we can extend it to get the full secret coefficients, and then from that we straightforwardly extend it to all coefficients of S. So if we've implemented this on a Raspberry Pi 2 as a cross-process timing attack. It works well, takes a few hours, and seems to work every time. Kyberslash2 is a little bit different. For this we will need a plaintext checking oracle. the idea is basically the following. You pick two messages that only differ in a single bit, and then you create ciphertexts, and then the ciphertext of those messages, of course, are going to look completely different from each other because the randomness will be derived from these plaintext, so they will be completely different. And that also means that the encryption time will be very likely different because of the leakage of that depends on the ciphertext. And what we can now do is we craft malicious ciphertexts that either decrypt to M0 or M1, depending on the secret. And then during the decapsulation, if we measure the time of the re-encryption, we can distinguish between M0 and M1, and that will help us to recover information about the secret key. This is a straightforward PC Oracle attack, nothing fancy in this actually. The only problems we faced in this is a little bit of noise, but that we can just run the experiment multiple times. That's very easy. The other thing that gave us a bigger headache was that actually we have Kyber/1 and Kyber/2 in the same code. So you have interference between these two. And the way we worked around this is that for Kyber/2, the ciphertext is going to be known. So we can pick messages that create ciphertext that have the best separation in timing between the two messages. And then we can actually make this attack much easier. So we run this on a Cortex M4 with that one attack setup where we do the timing on the device itself. So then you get really perfect timings, and then it's really straightforward. It only takes a few minutes. And then we try to extend this to also do a sort of remote attack where the timing is actually be done by a different Cortex M4 that sends over messages to the other one, and that also works fine. We just have to repeat it a few more times, but still within like 20 minutes we can recover the key. Okay, so how do we avoid this in the future? There's a couple of ways we can think about avoiding this. One way, and this was what was done in lots of implementations, was we rewrite the C code. So we eliminate these divisions, and then maybe in some other places we want to use some optimization barriers to avoid other timing leaks from being introduced, and then we hope that the compiler will not mess this up even in the future. That's not very satisfactory. So one alternative would be to write everything in assembly. Then you have full control, but it's going to be platform specific. It's quite a bit of work. So that's also not very satisfactory. Another option, which kind of complements the other two, is to test leakage of actual binaries. And one way to do this is using something like Wallgrind to test, and I'll talk more about that in the next slide. And then we just test this with lots of compiler versions, lots of different flags, and check the leakage of actual generated code. And that's something that we propose here. Another, maybe more long-term solution would be using formal methods, so using actual languages where there is some way to express that something is a secret. And then you can reason about certain operations not being possible on these secrets. So that's something that my co-authors have done with F*, and some other people in this room are doing with Jasmine. And you can actually do proofs of this. Let's start with Wallgrind. So this was first proposed by Adam Langley, and the idea is to mark secrets as undefined and then run Wallgrind on it. And then Wallgrind will complain in case you do a conditional branch depending on this undefined data, or if you do a memory access depending on this undefined data. And that's exactly two cases that we want to catch, and this works very well and has been deployed in a lot of places. So it's kind of the obvious idea to also add detecting secret-dependent divisions on this. So we patched Wallgrind to do this, and this works well. We can get the errors just like we would get them for the other two cases. very intuitive to use if you have ever used Valgrind to find timing leaks. And we've also submitted this to the Valgrind developers. So far, they haven't merged it. If anyone knows them, please talk to the developers. It would be really nice to get this upstream. That would make it much easier to use. But the nice thing about this is that we can just plug this into existing workflows that test constant time code. There's no changes needed. So then we've done a larger scale experiment on this and actually put it into TimeCop, which is part of SuperCop. And I'm not sure, I guess most people know SuperCop is a large collection of lots of different implementations of cryptography. And we ran it on all those implementations in there that are marked as constant time. We ran this on a relatively big machine, but it only took a little over an hour. So this really scales well. You can scan lots of different implementations easily. Few findings, there's quite a few warnings, but we looked into this in a little bit more detail, and the few interesting things are we managed to catch Kyber/1 and 2. We found similar code in New Hope. We found other divisions in HILA 5, and we found other divisions in Psych, although Psych now has bigger problems than divisions. Yeah, so this is quite easy to use, which we think is a strength of this. Reviewer 2 of another conference thought this is a great weakness because it's too simple. Luckily, CHES doesn't have Reviewer 2, so we didn't get this complaint at CHES. We actually use this in practice now. So we deployed this to a library that I'm co-developing called MLChem Native. If you want to learn more about that, my talk last Sunday at the Optimist workshop is online. You can take a look at that. But we do integrate this patched Valgrind in there and run it on lots of different compiler versions with lots of different flags on 2 platforms. So if you, and this actually runs in CI on every change. And we can look into this pull request. I re-added the Kyber/ vulnerability yesterday just to show how it looks like in CI. So if you have some CI that does constant time tests and you want to integrate this, please talk to me. It's very easy. Now, let's talk a little bit more about another approach. And this was actually how Kyber/1 was discovered. So some of my co-authors were writing a Rust implementation of Kyber based on the reference implementation, and then they were doing proofs in F* of this implementation. In F*, you actually have a type system that distinguishes between secrets and public values, and then it just disallows these non-constant time operations on secrets. So divisions and modular operations you can just not do on secrets. And also no branches and no array accesses. By now they've actually ported this to Rust, so they can directly do this in the Rust type system. And this immediately flagged Kyber/1. Interestingly, this also flagged Kyber/2 already in November, but the developers dismissed this alert because it was operating on the ciphertext, so surely that must be public. It's not public, so that turned out later that it's also a problem. Limitation of this is that this is still on the source level, so the compiler can still introduce timing leaks here, so you will still have to combine it with some dynamic testing like what I presented before. An alternative to this approach would be something like Jasmine, where you have a compiler that's secret aware and a language that's very close to assembly, so then you can get even lower level guarantees. Okay, let me wrap this up. So Kyber/ has been fixed in a lot of different places. We have sort of dodged the post-quantum cryptography disaster a few months before it was rolled out. I think this was quite lucky timing, and I'm very happy that we managed to fix this, or the community managed to fix this in so many places so quick. We showed that we can exploit it. We have practical attacks online. You can download the code and try it out yourself. We have some ways to catch this using Valgrind. The patch is online. It's relatively easy to use. And maybe formal verification is a more long-term solution to actually have crypto-aware tooling that avoids this in the future. With that, I'd like to thank you very much for your attention.
So, for the sake of time, I think just take one quick question, if any, from the audience.
Thank you for your nice talk and wonderful detail. So, what do you suggest to modify the compiler? I mean the compiler provider. How should a compiler provider to avoid such kind of problem?
Well, the compiler sort of needs to be aware of what is secret. And then certain optimizations that the compiler does should not be done on secrets. Mm-hmm. Sounds easy, but it's not easy.
Okay. So, for example, maybe we need to comment some variables to claim they are secret, or such that the compiler can know, or this cannot be optimized.
Yeah, you sort of need to annotate what are secrets and what are public. Mm-hmm. And then certain optimizations can only be done on public values. Yeah, this would be the ultimate solution, yes.
Okay, thank you.
So I think for the sake of time, we will stop here. Matthias is around, so if there are any questions, please feel free to ask him. So with this, I would like to say thanks to Matthias again. And so this brings us to the second talk, which is the runner-up talk. And the title of this talk is BIT TSNI Secure Multiplication Gadget for Inner Product Masking. And the authors of this paper are John Kaspos and Simon Duguay, and the speaker is John. So request John to come up on the stage.
Okay. All right. Hello, everyone. So first, I want to thank the program committee and the reviewer for giving us this nice recognition. It was a difficult work to do and to finish, so having that kind of recognition is great. So thank you for that. So this work is done by Simon Duguay and myself, John Gaspo. So as you probably know by now, side channel attacks are a specific kind of attack that target cryptographic device. So basically the device embeds a secret key and will use that key to make some cryptographic operation. But the device leaks information that can be voltage, that can be time, that can be many things, which depend on the secret data. So by analyzing this information, the adversary is able to extract part or the whole key. Note that in this work we'll be mainly interested in power analysis attacks, so just looking at the voltage. Against this kind of attack, there is a well-known and used countermeasure, which is masking. And the goal of masking is to make the power consumption independent of the security-sensitive information. So basically, if you have a sensitive value X, the idea is to transform that into a set of randomized shares. Here you have D+1 shares, and so we say that the masking is secure at order D. If you want to go from the set of shares to the secret value, in the case of Boolean masking, you will basically just do the XOR of all the shares. So throughout the years, a series of different masking schemes have been derived and described. Among them, some of them are using some simple encoding function, so how you make the shares. This include Boolean masking that just use the XOR function, or multiplicative masking that rely on the Galois field multiplication. On the other hand, you have different masking schemes that use a more algebraically complex encoding function. For example, you have polynomial masking, inner product masking, and code-based masking, which is more generic. Obviously, you're using a more complex encoding function, so you have an overhead compared to Boolean masking. But they show some nice properties, especially for software masking, which is what we're interested in here. Basically, they happen to decrease the information leakage observed in low noise conditions. And also they are more resistant to the physical effects, like the typical transition leakage that is a great problem in software masking. So here we will be interested in inner product masking. So IPM start with the setup phase, where you will define some public vector of d+1 value. The first value is always set to 1. And the other value, you can arbitrarily choose them as long as they're not 0. Now to make the shares, as always, you start to fetch some d-random values in the field. And then now to make the masking of your sensitive value, instead of doing directly the XOR from the secret and your randomness, now you make this Li times Xi multiplication first, and then you add it to the secret. Now if you want to decode, you just do the inner product between the vector L, which is public, and the set of shares. So because of the increased algebraic complexity of IPM, it allows lower leakages than Boolean masking. That means that these order IPM could resist higher order attack. And this is an effect that sometimes is called the security order amplification effect. To understand that first visually, you have the comparison between Boolean masking and inner product masking on a 4 bits secret value X. It's a 2-share case. So on the two masking schemes, basically you always fetch some random value x1. And for Boolean masking, basically you just do the XOR. So you see that each secret bit is correspondingly masked with the same bit of the secret. So A is masked with A1, B with B1, and so on. Now on the other hand, with inner product masking, you do this multiplication. And that means that you start to mix more random bit, more bit of the randomness to each bit of the secret. So now you see that, for example, the secret bit A is masked with C1 and D1. And that means that if you want to reveal just a single bit of secret, now you will have to probe, for example, A0, C1, and D1. So you have some kind of amplification. And so that's a nice effect. But with the existing gadget, it only works on the encoding. And basically, as soon as you start to make secure computation, like nonlinear operation, you lose this benefit and you go back to the same security level that you will have with Boolean masking. And this is because the gadget, they are currently defined to maintain the word level security and not the bit level security order. So our goal in this paper was to define a new multiplication gadget for inner product masking that preserved this bit probing security during the secure computation. So you maintain this amplification of the order during the computation. We wanted to have some composability in mind, so we followed the T-strong non-interference property in the bit probing model. And we want to back all our results with formal evaluation and practical evaluation. To go now a little bit more formally on the secure amplification, basically this comes from Poussier et al. Work, where to understand this amplification, we have to connect inner product masking to yet another masking scheme, which is direct sum masking. And basically, direct sum masking works over bits. It is connected to code-based masking, and basically, if you want to make this sharing of Z here, basically you have a set some sensitive value X, some set of random value Y, and you make this operation of X times G plus Y times H, where G and H are two generator matrices that makes these two code words C and D. Now, basically, if you want to connect them, you can see that depending on how you define these two matrices, G and H, you can connect that to inner product masking. So basically, if you define the matrix H to have this first column to be containing these Li values and then an identity matrix, this is the equation that will produce an inner product masking encoding. And they show that the bit probing security of direct sum masking is equal to the dual distance of this matrix H minus 1. So that means that for inner product masking, the best bit probing security can be achieved by selecting this vector L that maximizes the corresponding matrix H. So as you guess, we distinguish two levels of security. We have first a standard word level security. So we allow one probe to reveal a full share, like a full word element. This is evaluated under the standard probing model, so it's the number of shares n minus 1. Now, if we go on the final level of security, we go on this bit level security. We allow any probe to reveal just a single bit. And well, this has been connected, as I showed before, with the dual distance of this code minus 1. And basically, the security in the bit probing model, it implies security in the bounded moment model with the same order of security. And this is what you typically evaluate when you do a TVLA. Obviously, the word level security cannot be higher than the bit level security. So what can you expect from optimal codes for IPM in terms of amplification of the security order? You see that for already 2 shares, which is n, sorry. If you go with 2 shares and 4-bit elements, you already reach second order of security on the bit level. So you gain 1 extra level of security compared to the word level, or just compared to Boolean masking. Because Boolean masking will always have the same bit and word level security. And this increases up to 7 order of security if you go for 3 shares and this 8-bit field case. So this is something you would like to have for your computation. We have some security definition. Basically, we follow the non-interference and strong non-interference. Basically, we said that the gadget is T and I. If you have a set of T1 probes that you place inside the gadget and a set of T2 probes that you place on the output of the gadget, and basically you have T probes, and all the probes in the NI case can be simulated by T shares of each input. Now we go with the strong non-interference case, which is a little bit the same, but now basically the totality of the probes can be only simulated with T1 shares of each input. That means that whatever you probe on the output doesn't propagate back, and then you can have some composability reasoning. So this is the multiplication gadget. This is a case with 2-share masking. So it takes some input x, some shares of y, and you get the output that equals to x times y. It works in 3 parts. So in the first part, basically, you have to define and compute what we call refresh matrices. So this is quite a heavy task. Basically, the refresh matrices are using a dedicated gadget that makes encoding of a value 0. And since it's quite heavy, we kind of do it in a pre-processing phase or like offline phase. And basically, in the next stages, we can simply get them by some memory access. I'll go a bit later on the exact definition of those matrices. But basically, in the part 2, this is where the actual multiplication between the shares happen. We have this specific mult gadget that takes 2 shares, takes the refresh matrix, and makes the secure multiplication. Then we have the usual third part where we do the compression. Basically here it's the usual, we have 4 cross product, we want to go to the 2 output shares, so we do that kind of unmasking at that point. We do this multiplication time L and then the XOR. So for the actual multiplication between 2 shares, basically in order to have this bit SNI security, the multiplication of the shares in this field now needs to be operated securely at the binary level. And if you look at the multiplication of like x0 and y0, and you take this Colebook multiplication algorithm, you just like you take 1 bit of x0 and you multiply that to each of the bit of y0. Then you do the shifting, you take another bit of x0 and you do it with all the bits of y0. And then if you have an overflow, you do the reduction and so on. So basically now we need to securely mask each of those binary cross products while still preserving at the end the correctness and word TSNI security in the field. We need to handle as well the reduction with the reducible polynomial that you pick, and that's it. So this is the detail of the gadget. It takes two shares like xi and yj. Now basically we look at them as a vector of k bits. Then the first step we do is that we do this Colebook multiplication. So we compute all these binary cross products. What we get at the end is this C-tilde matrix. That now if you just do the XOR of each of the rows, you get back to xi times yj. So we're always staying in that kind of binary matrix. Now we do the refreshing. So we get our refresh matrix S. You already see a little bit how it's made. So basically it's made by some specific composition of this gadget called IPM0, which produces shares of encoding of a value 0. So now we have refreshed, and then we need to compress again. So we do this XOR, and we got our element. I'll go through a whole example. It's pretty quick. It's for 2 shares and 3-bit elements. So here you really see how we generate those matrices. So here we have 4 cross products, so 4 refresh matrices. And so first we fetch 12 two-share IPM of this gadget 0. We take the half of these, so S0 to S5, and we place the first share in the first matrix, and the second share in the corresponding second share in the second matrix. Now we iterate the same process for the second half from S6 to S11, so first share in the third matrix and the corresponding second share in the last matrix. We then fetch six two-share IPM0 that we call Ri, and then we distribute, like as you see here, so the first share in the first matrix and the corresponding second share in the third matrix. Then you can go to the multiplication. Nothing very special here. So the school book multiplication, we make the multiplication to each of the bit of x0 to all the bit of y. Then we need to remask, so we get our refresh matrix. You see on the word element how it's made and then how it can be visible or seen on the bit level. We just do now the XOR of the two. And basically now you see that each row is now masked with an independent share. Basically then we do the XOR of each of the row and we go from this bit vector to the field representation. What you get at the end is the field multiplication of x0 times y0, plus then some sum of those first share SI value and some sum of those first share RI values. Now if you iterate that for all the cross product, this is what you get in part 2. And basically in the last part, the third part, you do this compression phase. And what happens is that all the SI shares, all their corresponding first and second share, so they get decoded to value 0, so they cancel out. And what you get at the output is still something that is securely masked with some RI values. We formally prove that to be SNI in this bit probing model. The proof is quite heavy. We try to make it clear, but if you want to have some good time, you can look at it. Then we went to look for algorithmic efficiency. So basically what we wanted to compare is our multiplication gadget, looking at the number of AND gate in blue and XOR gate in green, comparing to Boolean masking using ISW for the multiplication. So the straight line is for Boolean masking, the dashed is for our work. And we want to evaluate how that will increase with the bit security order increasing as well. And well, with Boolean masking, if you want to keep up with that kind of security, you always have to increase the number of shares. So you keep increasing and increasing, but with our gadget, basically, you can maintain this property, so you have the security order amplification. So you start to use less number of gates at some point, like you can see on the fifth order of security for the 4-bit element. So that's a nice result, but we need to temper that with the cost of generating this IPM0 gadget. So you saw that we used that kind of encoding of 0 to refresh all our values, and basically we need this gadget to be as well T-order probing secure. So to make that kind of gadget, basically what we do is that we create T plus 1 regular encoding of 0, and then we XOR them together. Actually, you don't really need a T secure, but you can use a T minus 1 secure, that's sufficient. But what that means is that now the cost of one of this call of the gadget, it requires T times the cost of sharing a 0 value. So that's quite heavy, and the randomness cost is not free. With Boolean masking, you just get the shares and the randomness, and that's it. Now we need to make this operation first. So there is a high cost of randomness generation required, which is currently the bottleneck, and this is why we said, okay, you can do that in an offline phase and then just fetch it when needed. We believe, obviously, that some optimization might be applicable to that. We completed our algorithm evaluation with the practical efficiency, looking now at the cycle count. So again, with increasing bit security order, we compare our work with Boolean masking ISW. For the actual multiplication, we distinguish the school book multiplication or the usual log-a-log optimization that you can do in software. And again, because we have this security order amplification, we start to use even less cycle counts compared to ISW log-a-log, which is nice. But again, if you take into account this cost of randomness generation, it kind of blows up. We wanted to have some practical leakage detection, so we made an ARM assembly implementation on the 4-bit elements for Cortex M4 core. It's a two-share implementation that we expect to be second-order secure. So we do the first-order evaluation, then we went for the second-order bivariate test. We use the center product to make that preprocessing. And basically the thing is, well, in software the traces are very long. So when you try to do this second order, you start to have too many points. So basically we use some careful downsampling when we keep 1/5 points. And then according to Dingedal, we follow this, because even with downsampling, you still have a lot of points when doing the bivariate test. So we increase the threshold value a little bit in order to avoid this false positive that can arise with that many points. This is the result of the evaluation. So we have the first order evaluation, nothing very special. We expected it to be secure, and it was secure. And then on the right, you have the bivariate evaluation with different public vector L. So on the upper left, you have the L11. This is identical to Boolean masking. So obviously, as you can see, it leaks. It's a little bit tiny, but there are red points here and there. And then we went with the L12, which from the theory is not second order secure, but you start to mix a little bit more of the bits of the randomness. So we expected it to leak a little bit less, but still get leakage. This is what we still see. And then finally, we go with the theoretical value that will produce this second order of security, and we evaluate that, and we didn't have any leakage points for 1 million trace. Well, if you were at the RAM session yesterday, there were like this poll about how much trace is enough. The thing is, like with software masking, if it leaks quickly. And with 1 million trace is kind of good enough to be reassured. And the last plot is just with the randomness disabled, so you see like the setup is correct, it leaks everywhere, so yeah. What we checked as well is the evolution of the max peak value, so the T value. And well, if it leaks, you expected it to keep increasing more and more as the number of traces that you collect increase as well. So you see on the bottom, you see these two wrong parameters, L11 and L12, and you see that the value keeps increasing more and more, whereas with our secure parameters, L16, it stays somewhat flat. So to conclude, we make this TSNI secure multiplication gadget for IPM that preserves then this security order amplification during secure computation. We have lower number of gates compared to Boolean masking SW multiplication in the online phase, but then we have a heavier processing phase compared to Boolean masking. We went to also make some side channel evaluation. We didn't have any leakage on 1 million trace. The code is online. If you want to look at it, play with it, or use it, that would be nice. And last slide, some future work. Well, obviously, there's this issue with the randomness. We can always try to reduce the cost, the randomness cost of this IPM0 gadget. We'll also try to reduce the number of instances that are required in the multiplication gadget. We made the implementation because I think it's important to have some actual tests on the gadget. But the gadget was not made to be very efficient, was made to be usable at first and working. And what would be nice is to have an extension to code-based masking, because now the gadget is really tailored for inner product sharings. So it's not compatible with the more generic code-based masking. And in that regard, on this simplification of security, code-based masking is really great because you have more flexibility on how you make those generator matrices. So you could maximize this, this property. If you're interested into that kind of stuff, you can come to the masking software session this afternoon. I will present that, that extension work. That's it. Thank you for your time.
So, time for some questions. So, any questions from the audience?
Thanks for the very nice talk. Is there a security order threshold for which the randomness requirement with the current version starts to be better than for Boolean masking?
Sorry, say it again.
So you, for the number of, for the complexity, you did a curve showing how you need this security order to be more efficient than Boolean. Could you do the same for randomness requirement?
The thing is, the randomness that we use, it's huge, so we have to call this IPM thing more and more and more. So I guess you will always lose for the moment with the existing gadget compared to Boolean masking in that regard, yeah.
Okay, thank you.
There are more details in the paper on that, by the way, if you want to look.
Thanks for the great talk. Regarding composability, you rely on SNI, so you probably cannot get around using refresh. Do you have a refresh gadget that is compatible, or can I use any that's SNI?
So it's SNI, so you will have to use this refresh, otherwise you'll have problems.
But I can use the same ones that I use for Boolean masking, or something specific?
I think we didn't look furthermore into what you will have to make the whole thing. So I guess you can always try to derive that kind of construction that we did for the refresh matrices, and then use them just as is to as a refresh gadget.
Okay, thanks.
Any other questions? So I was just having one thought that, I mean, like, did you also like, do you also think that faults can be an interesting thing to look into in this context? Like, because people have used faults for analyzing, you know, like Boolean masking. So
Yeah, I think it may be interested. It's just not exactly my field. So maybe someone in the fault topic would like to pick it up. That would be nice. But maybe there is some ways. In the code base, also code base is often used for that as well. So maybe that can be also useful in that regard.
my question was like, do you think that the vulnerabilities would be like similar to Boolean masking, or like, do you anticipate any differences?
With faults, I have no idea. Sorry.
Okay, any other question from the audience? Okay, if not, then let's thank the speaker. Okay. So this brings us to the end of this session. So I think we'll take a break and go to the next one.